Morning all. Hope everyone's well. So the final part of Chemistry 2 today. This has actually ended up being a 4-part lesson rather than sort of 2 or 3, which the other ones have. But it's quite a big topic and it has links to lots of other areas. So I definitely felt it needed to be done. Morning Tanisha, good to see you online. So what I want to do today then is we're going to look at metallic bonding. We're going to finish off sort of that particular area because that's really the sort of the final part of the bonding side. We're going to go back and have a look at some key stage 3. Morning, Amy. We're going to go back and have a look at some key stage 3 states of matter, but we're going to put a key stage 4 spin on it. And we're going to bring in the sort of kinetic theory and link that to some of the sort of intermolecular forces that we've been talking about up till now. I then want to have a look at nanoparticles and nanoscience and this whole sort of surface area to volume ratio, which always makes me chuckle when I start getting students to try and calculate that, because it's actually quite basic maths, but for some reason everyone's brain seems to sort of dribble out of their ears at that point and they struggle calculating sort of surface areas and volumes. So we'll go back and have a quick look at that, and then I'll explain why it's quite important that we can do that. Morning, Chris. Good to see you up. So we've looked at ionic bonding, which we said was between metals and non-metals. We've looked at covalent bonding, which we said was just between non-metals, and they will either form small molecules like carbon dioxide, like water, hydrogen, those sorts of molecules, or they can form our sort of giant covalent molecules, which will form so things like diamonds and graphite, and even nanotubes to a point. Even though they're quite small molecules, and we'll look at what this word nano means later on in the lesson, we've still got this idea that actually it's still a big molecule in comparison to things like water and carbon dioxide. A lot of the plastics that we look around us, so we looked at polymerization, and we said that actually plastics are another giant covalent molecule. Ionic molecules, I mentioned at the beginning, they are also giant as well, so they're huge molecules. So we don't talk about intermolecular forces between ionic molecules or giant covalent molecules because they're all one big molecule. So we don't need to worry about the forces of attraction between them, because actually things like mass and gravity and sort of the weight of them is more important than those intermolecular forces. So the intermolecular ones, the sort of forces between molecules, only really comes in when we look at small covalent molecules. So let's get started then. Today, I said we're going to start looking at metals. So we said we've got metallic bonding. And hopefully the clue's in the name. This is only between metals. So if you are making up revision cards and you are making up sort of cheat sheets and things that will help you remember this one, metallic bonding is just between metals. And in some respects, it's the easiest bonding. We don't have to worry about drawing out lots of electron shells. We don't have to worry about electron transfers. There's no ions formed at all with metals. But I think we often gloss over metals a lot quicker because it is simpler, and students then end up with a sort of less of an understanding of it than they should do. Ionic and covalent, we have to actually think about. There's lots of different molecules that we need to draw out, and we need to be able to know how to draw them out and then explain those properties. Whereas metals, we haven't really got that. We've got one type of structure at GCSE that we need to know. Now, the structure of metals is pretty much your your Key Stage 3, or even Key Stage 2 for some schools, solid diagram. But we're not going to draw them touching to start with. And I'm actually going to drop in a picture here. So let's just do that. And this is the one that actually is given to you in the specification by AQA. So I've literally taken this straight from there. And it should be that one if it's going to show up. There we go. Now, what we've got in this diagram then, and they are two sort of diagrams that realistically show exactly the same thing. This is your sort of typical Key Stage 3. We've got our circles in a solid and they're sort of lined up. We are looking at a sort of giant lattice structure in the same way as when we're looking at ionic. But we've got these sort of molecules, they're lined up. However, with metals, all of the electrons are delocalized. So we have lots and lots of delocalized electrons. Now, it's quite important to get your head around this next bit because it has some major ties when we start looking at electricity in physics 2. If we can't understand the delocalized electrons and how they move through the structure, it's really difficult to try and understand what resistance is and what current is. So again, this is a tie to one of those other lessons that we can sort of bring in, and I'll come back to this in physics 2, just as a bit of a recap. Now, this particular molecule shows we've got this sort of positive nuclei with these electrons around the outside. If you remember back to chemistry 1, you'll realise that actually this is quite a poor representation because the nuclei itself is only about 1/10,000th of the size of the atom. So it's very, very tiny in the middle. But we wouldn't be able to show that on a representative scale in a diagram like this. So we draw the molecules in this way. So we've got this idea then that we've got this positive nuclei with electrons around the outside. But because the electrons are delocalized, when we draw them as a sort of as a solid, as this lattice, we don't have to think of them in sort of fixed electron shells or in these energy levels. We can think of them as free to move through the structure. So in some ways, this is almost a better diagram when we're trying to explain the properties between the properties that metals have. So we've got all of these delocalized electrons and we have these positive nuclei. Now, we should be getting quite familiar with looking at the sort of the reason why these solids form. I don't mean in terms of full shells, because we don't need to go into that with metals. They're all sharing electrons in a similar way to covalent, but they're not fixed. And we're not going to sit there and look at how we know they've got a full outer shell, because a lot of the structure of metals is actually the transition elements in the middle. And the electron configurations don't follow the same 288 rules once we get past number 20, so calcium. So we can't draw out the electronic configuration. That's very much something we do when we go to A level. And again, it's something, if you want to go through it, it's absolutely fine, but I'm not going to cover it in this session. I can either do it in a separate session later on, or we can wait till we're back to school, and we can sort of go through some of the more advanced bonding then. But for the moment, all we need to know is these electrons are delocalized. Because of that, we should end up with this idea that we've got these opposite charges which attract. So there's a strong attraction between the positive nuclei and this sea of delocalized electrons. And again, in the same way as magnets, they're all going to stick together, they're going to be attracted together. So we could also say, in the same way as we did when we've looked at other solids or other materials with high melting points, that we're going to need lots of energy to break or overcome. So therefore, we're looking at high melting points and boiling points. Now, the strength, or the size of that melting point and boiling point, and the strength of those forces is very much going to be dependent on the nuclear force. So in other words, how positive the nuclear is, or I should say, how many protons the nucleus is, because the more protons, the greater that nuclear charge. So let me just change colour again, just so we can put this down here. This, so we could say the size is going to be sort of proportional to the nuclear charge. The size of the atom, or we could talk about the number of electrons. Now, you're not going to need to explain too much about that, because again, that's edging up into A level. But you do need to be aware that actually they could ask a question, and we could link it back to the nuclear charge. Because realistically, if we've got a stronger negative charge and a stronger positive charge, those atoms are going to be attracted more strongly to each other. That's going to mean we're going to require more energy in order to break, which is going to increase the melting point and boiling point. The problem also we've got though is if the molecule starts getting too big, then actually those charges get a bit further away from each other, which will lower it again. So there's lots of sort of conflicting factors here. So don't panic about it too much, but it is something that's worth being aware of. And it could be a sort of grade 8, 9 question in the exams, where they could give you some data, and whereas you wouldn't have to go into too much detail, you might be forced to try and make a judgment on how it would affect the melting point and boiling point. And as long as you can justify your reasons and the reason, so for why you think it's changed, and you would link it back to that sort of nuclear charge or size of the atom, it'd be perfectly fine, because they're not expecting you to have an in-depth knowledge of it at this time. So we've got this idea of these opposite charges attract, lots of energy required to break those charges. And if we think, and I'm going to come back to this in a minute when we look at states of matter, what we're trying to do is get those atoms to vibrate fast enough that we can actually cause them to slide past each other and actually break those forces. In the same way as that when we want to separate two magnets, we've got to put energy in and force in to pull them apart. That's what we're trying to do. Now, the other sort of factor we can have a look at when we're looking at these, we just scroll down slightly, is with these delocalized electrons are going to be free. Oh, press the button. Let's just zoom back out. These delocalized electrons are going to be free to move through the structure. So in other words, they are going to be conductive, and that's going to be conductive to heat and electricity. Now, it's quite important that we understand that it's not just electricity here. Obviously, if we connect this up to a battery and we create a difference in the potential, so there's potential difference between one part of the metal and another part, then the electrons are going to move away from one potential to the other. So we're going to actually carry this charge as the electrons move through that structure. So we've got that idea there as well. But the reason that metals are very good conductors of heat isn't anything to do with the fact that the atoms can vibrate and pass on that energy quicker than in insulators, because that's not really the case. It's the fact that when we start heating them up, the electrons can actually move, and the electrons can carry that heat energy as well. So the electrons move faster, they can move throughout the structure. So in other words, that energy is carried much, much faster. So it's worth having that in your heads when we come back to energy again in physics, because when we look at the difference between conductors and insulators, the reason the metals do that is because the electrons can move. It's not because the atoms can conduct or pass on that energy any faster. Now, when we look at physics 2, we've got this idea of resistance. So we've said the electrons can move through the structure, but every time the electrons are moving through, there is the opportunity for them to collide with one of the nuclei. So the nuclei can get in the way. And that's all resistance really is. It's those electrons trying to move through, be pushed through by this potential difference caused by a battery or power pack. But as they're moving through the structure, they're trying to go in between those nuclei. And every time they hit one of those nuclei, that is the same as causing resistance to it. Now, if we increase the temperature of the metal, we're giving those particles energy, so they start vibrating more, which means the likelihood of one of the electrons colliding with the nucleus goes up. So we've got a higher resistance for it. So we'll look at this again with physics 2, but that is the reason why we get resistance, and also why resistance changes with temperature for most materials. So let's just go back over to this side. We've looked at melting point, we've looked at boiling point, we've looked at conductivity. Now, if I look at this diagram again, we can see that these are all in layers. So one of the benefits of using metals to build things out of is we can actually mold them to different shapes. So we can heat them up, we can hammer them, we can bend them into different shapes, so cars, saucepans, whatever we want to make with them, realistically we can shape it with metal. And that's because if we apply a force to these layers, so let's just apply a force to it, what's going to happen is the layers are going to slide over each other. So we actually end up with these layers shifting, and that enables us to mold it. And the name of this property we call is malleable. We can also extrude, so we can also push metal and sort of draw it out into a wire, so we can also call it ductile. And that is literally just because these layers can slide over each other, which is what makes them useful. The problem is, for some metals, it also means they are then too soft for us to do much with. Pure iron is still quite strong, but if we wanted to build something in terms of construction, so cars, bridges, like that out of pure iron, it would bend fairly easily under the weight, under the forces involved. So we've looked at and in fact we actually found this out quite early on, ways of making it stronger is to mix things in with it. So iron itself, and this comes up much later on, but iron itself is extracted in a blast furnace. Now, a blast furnace basically is where carbon is used to get the iron out of rock. So iron is found in rocks, is iron oxide. So it's bonded with oxygen. Now, you can go back and you can look at the ionic formula. You can look at how this sort of forms. But the formula for iron oxide, or one of the formulas for iron oxide, is that. And in order to get iron out, we need to get rid of this oxygen. And we can do that by mixing it with carbon. Now, what they found out was that some of the carbon afterwards is left in, and we end up with cast iron. And cast iron is much, much harder than pure iron, but it's also more brittle. And this really was the sort of first alloy, or sort of one of the alloys they came up with in the Iron Age. Now, before that, in the Bronze Age, they also found out that mixing metals together to make bronze, you'll notice bronze isn't in the periodic table. We consider it a metal, but it's actually a mixture of different metals. And they would have mixed these metals together, melted them down to form something that's significantly harder. So we've actually been mixing metals for quite a long time. So the definition of an alloy is just a mixture of different metals, or carbon, so other elements as well. And what it does is this: it disrupts. So we've said up till now we've got a metal as in discrete layers. This is assuming that the atoms are all the same size. But if I start mixing elements in, or atoms in, that are different sizes, then straight away I just draw out and just put a couple of these in. Straight away, these layers are no longer nice and neat, which means if I try and apply a force to it now, the atoms are sort of going to jam up and the layers are not going to be able to slide over each other as easily. The electrons are still delocalized, so it still conducts electricity, but now we actually have something that is much harder. And what we end up with is we've got with steel. So let me just put this down. Steel is literally when we mix iron with carbon. With steel, how hard the metal is depends on the amount of carbon we put in. The more carbon, the harder it becomes, but also the more brittle it becomes. So we end up getting this fine balance. And actually, we've got thousands of alloys that we use on a daily basis now. Most bikes are also made out of alloys of aluminium. When we're talking about alloy wheels for cars, again, it is made of aluminium, but aluminium is quite soft and easy to mould. So we'll mix other metals in with it to turn it into an alloy. If we want to make stainless steel, then we've still got iron and carbon, because actually that's what the term steel means. But we also mix chromium and other elements in with it in order to increase the sort of, so it doesn't corrode. So this idea of an alloy is literally when we just mix different metals together in order to combine some of their properties, but usually to increase the strength or the hardness of it. Okay? So let's just move that down. So that's pretty much it for metals. We've just, as long as we can link that structure back to those properties, that's the main thing. And again, when we look at the alloys, make sure you can talk about the increase in strength, but also the increase in hardness and the making it more brittle. So it's just worth having that down. Again, any questions, put them in the comments box. If I sort of waffled or not made any of that clear, just let me know, because I can go through any of that again. So we'll have a look at now, while I wait and see if any comments come up, we're going to have a look at states of matter. So this bit should be revision. However, what I'm going to link it to is I'm going to link it to kinetic theory, because it's really important that we've got our heads around what kinetic theory is, because it comes up in chemistry and physics, and we've got to make sure that we properly understand it. It actually comes up a bit in biology as well. So states of matter, and as I said, this is just revision. I'm not going to pretend that any of you shouldn't know this. Some schools cover this in primary. We know that if I was to ask you to draw out what the particles would look like in a solid, we're going to draw a nice, neat, ordered row of particles. We're then going to have our liquid. Now, this is one of those areas, and apologies to primary school teachers. Lots of primary school teachers draw a liquid as similar to a solid, but with gaps between them. This is a gas. This is not a liquid at all. With a liquid, the particles are still touching. Okay, so we've still got this idea that they're close to each other, but they've now got enough. They're now moving quick enough that they can slide over each other. Hi, Tanishka. Yeah, sorry, just go back. Transition elements are all metals, but they generally have slightly different properties to groups 1 and 2. They're much, much harder. They have higher melting points. So yeah, I'll come back to that in a bit if you want me to, but they're all metals. So I've got my solid. I've got my liquid. And I'm going to put a gas down here. Oh, there we go. So make sure you got this right when you're putting these down, in terms of the idea that with a liquid, the particles, they're not nice and neat and ordered. Both liquids and gases are fluids. I know we often talk about fluids being liquids in terms of water, but both liquids and gases are fluids because they can mold themselves to their containers. But liquid, they're still touching. Gas, they've moved apart. We know that we're going this way. We have melting. And we have evaporation. And if we're going that way, we have freezing. And if we're going that way, we have condensing. So none of that hopefully should be new to you in any way, shape or form. Now, where kinetic theory comes in is we've got this link between the movement of particles and the temperature between them. So this will come up a lot in physics. I'm only going to cover this fairly briefly now, but we've got this idea that in order to go from a solid to a liquid, the particle is going to melt, but we also need to increase the energy. So going down this way, we're increasing the energy. And if you... Morning, Olivia. And if you think back to what I've been saying in terms of the intermolecular, intramolecular forces or the bonding, the amount of energy required depends on how tightly these atoms or molecules are bound together. So it could be atoms sliding over each other, it could be molecules sliding over each other. But what we're looking at here is we are giving enough energy to try and overcome or break the forces or the bonds, depending on the material we're looking at. Now, we increase the energy, go this way, we increase the energy, and I can put this down here, by increasing the temperature. And again, that shouldn't be new. There should be things we know. It's just making sure that you've made these links in your head so that you can actually talk about it in exam questions. So there is a direct correlation between the temperature, the energy, and the speed the particles are moving. So if we increase the temperature, we are giving those particles more energy. We are transferring energy into them. Remember, we can't make or destroy energy. So we're taking it from one place and we're transferring it into those particles. And whenever we give particles energy, they will start vibrating or they'll start moving faster. When those vibrations or those movements become fast enough, then they can start breaking those bonds, or they can start overcoming those forces between them, and they will either melt, or in the case of a gas, they can actually physically break away completely because they're now moving fast enough to fly away and start bouncing around the room. So, and the size of those forces and the amount of energy they need depends on, the amount of energy they need and the speed they need to be moving depends on the forces between the atoms and the molecules. Now, kinetic theory also goes the other way as well, in terms of anything that makes the particles move faster means they must have more energy, so the temperature goes up as well. So if you've ever used a bicycle pump to pump up bicycle tyres before by hand, as you're moving it, you often notice that the bicycle pump itself gets hotter. And that's because what you're doing is every time you're pushing that piston in the bicycle pump down, it's hitting particles, which is making them move faster. And because they've moved faster, they've gained energy, so the temperature's gone up. So we can look at it in both ways. But in the future, when we start talking about kinetic theory, this is where I'm going to be coming from. Okay? So we've got this idea, more temperature, more energy, the particles move faster. When they're moving fast enough to break those bonds or overcome those forces between them, then we get a state change. So we get a transition from a solid to a liquid to a gas. In some cases, the size of the forces needed to break the bonds in a solid and to break the bonds in a liquid are so close together that we don't actually get melting happen, we get sublimation happen. And sublimation is where we go from a solid directly to a gas. So if you've seen the sort of dry ice on films and on stages, that's basically where they'll have solid carbon and it's subliming directly into carbon dioxide gas that's being given out, but it's still quite cold at that point. Okay, so we've got that idea as well. So that's sort of the states of matter and the kinetic theory. We will be coming back through this in physics though, because it's sort of quite a big area of physics where it's quite a small part of chemistry, but it's worth noting. Right. Now, nanoscience. So when we were looking at allotropes of carbon, so last lesson maybe, I think it was last lesson, so Monday, when we were looking at the allotropes of carbon, we mentioned nanotubes, and we said that nanotubes is a sheet of graphene that's been sort of rolled up into a tube. We can also make fullerenes, or we can make sort of cylindrical objects that are sealed at the ends. So we've used this word nano, and we haven't really clarified, or I haven't really clarified what it means. So we're going to start looking at sort of nanoscience now, and that's pretty much going to finish off the lesson today. So we may not take the full hour, we'll see how this goes, but we do need to make sure that you've got your heads fully around what this idea of nano means. So in terms of chemistry, nano is when we're looking at any molecule or particle that's in the 1 to 100 nanometer range. Now, you're probably looking at that going, yeah, that still doesn't explain to me what a nanometer is. That's absolutely fine. We know that 1 meter, so we know what a meter is. We're used to using meters. We've used it in schools. That shouldn't be anything too new. We know that actually a meter is made up of 1,000 millimeters. So in other words, 1 millimeter equals, and the better way of writing this, and you must get into the practice of putting this in standard form, equals that. So these are all the same way of showing 1 millimeter. So in order to go from 1 millimeter to a millimeter, or to our measurements here, we would divide by 1,000. So working our way down, we're going to divide by 1,000. Now, if we divide by 1,000 again, we end up with a micrometer. So there is 1,000 micrometers in a millimeter, or 1,000,000 micrometers in 1 meter. So 1 micrometer is 1 times 10 to the minus 6 meters. If you are struggling with standard form, go online after this, do some research, look on Seneca, look on Hecate Maths if you've got access to that, YouTube, but go and do some revision around standard form. It's coming up more and more in science, and because there is a massive increase in maths demand in science as well now, you've got to get your heads around that. So the power of the 10, Tanishka, this is standard form. So I've got 1 times 10 to the power of minus 3. That is the same as writing this. If I want to write this one, 0.00, okay, I could write it like this, but we end up with lots of zeros. And actually, as numbers start getting smaller, and we end up with more and more zeros, it's not actually feasible to keep writing out like this one. So we often go to standard form. One of the numbers that's going to come up when we do the next chemistry topic in sort of a few weeks' time is Avogadro's number. Now, Avogadro, 6.02 times 10 to the 23. So I couldn't actually write a number out with 23 zeros on the end. so we write it in standard form. So this is one of those topics, if you're not familiar with standard form, go and do some research after it. I'm not going to do a whole session on it now because actually it will take too long, but you should have been through standard form in maths, and I will clarify with the maths department later on just to make sure they have. I might even get them to set some extra work on that just to make sure that you guys have got your heads around it, because it's really, really important in science. Okay, so 1,000 millimeters in a meter, 1,000,000 micrometers in a meter. If I divide by 1,000 again, we end up with a nanometer. Okay, so there are 1 billion nanometers in 1 meter. So 1 nanometer is 1 times 10 to the minus 9 meters. So generally in science, a lot of time people can get their heads around different concepts. The ones that they can do, but they really struggle to understand, and I completely get this, is when we start looking at either very big numbers or very small numbers. So if we're looking at space, for instance, we're generally looking at numbers that are so huge that we really struggle to try and comprehend it. When we start looking at distances in space, we generally start looking at things like light years, or even if we start looking at the size of planets and size of stars, these numbers get absolutely monstrous, and it's so hard for us to try and understand that. On the other side, if we go and have a look at very, very small objects, again, it's really, really hard for us to try and comprehend. We can picture a meter, we can picture a millimeter, because we can see them. We can see them, we can manipulate them, we can measure them, we can do things with it. But if we start getting down to things like a nanometer, so we're looking at 1 billionth of a meter, or even a millionth of a millimeter, actually our brains can't see it. They can't physically work out what that represents. But that's what we're looking at when we're looking at the nanometer scale. So it might be something, and there's a few YouTube videos on this one, where they look at the power of 10, and they actually zoom in, and then zoom out as well. So it might be something you want to have a look at, and if you would like, I can put a YouTube video up linked to this later on Google Classroom, so you can see the video I'm talking about on this. But it is quite difficult to comprehend. Working with it and explaining what's going on, that bit's easy, but trying to physically visualize this does get quite tricky. And that's not just for you, that's for adults, that's for scientists, that's for everybody. Because again, we're so used to dealing with things that we can see and manipulate, and we can't see and manipulate on that level. Okay? So, if you've struggled with standard form, and this is still not making any sense, do some research on this one, and feel free to email me afterwards, and I'll see what resources I can find. But I know there is work on Seneca, I know there's work on Hecate, and there is entire YouTube videos devoted just to working out standard form. So it is well worth trying to get your heads around and spend a bit of time learning it now, because what you don't want to do is have to think about it in the exam. You just want to be able to write numbers in standard form. Okay? So when we're looking at nanoscience, we're looking at anything that's within sort of 1 to 100 nanometers. Generally speaking, this is molecules that contain a sort of few hundred atoms. So we are looking at things that are very, very tiny. Now, you're possibly looking at this going, okay, but that's all well and good, but why is he spending time talking to me about this? So one of the things we look at is the properties of materials. As often depends on the sort of surface area to volume ratio. And actually, a lot of materials, when we end up with a very high surface area to volume ratio, in other words, when we start working our way onto the nanoscale, the properties of that material physically changed from the macro scale. So we end up with something that's behaving in a completely different way. And that's really useful. It also means that in some cases that if we want to try and do something with it, because they become much more effective, we don't actually need very much of them. And I'll show you some examples of that in a moment. Now, you do need to be able to calculate surface areas and volumes. And those of you that I teach, you'll know that I've probably done this exact same problem with you in class. Mostly, students get it wrong because they're used to doing things that are more complicated. And it's always quite funny when we get people to try and work out surface area and volumes of cubes, because they generally get the two mixed up, or they just give me something that's completely random and guessed. So I'm going to go through it now. And apologies, those of you that I teach, you'll have seen this before. But if we started off with... Actually, let's just move that down to there. I'm going to have a cube. And I'm going to just sketch this next bit in. So it won't be exactly to scale, but I'm just going to sketch this in now. We've got a cube. And we're going to say this cube is 10 by 10 by 10 now. Now, the number of times I've said to students, what is the surface area of this cube? And they've turned around and gone, it's 1,000. It is not 1,000. Okay? The volume is 1,000. Because the volume 10 by 10 by 10 is going to equal 1,000 cubic centimeters. Make sure you get your units down when you are doing this. The surface area, though, is the area that's in contact with the outside. So in this case, we have 6 faces, and each face is 10 by 10. So each face is 100 square centimeters, and there's 6 of them. So the surface area in this case is going to be 600 centimeters squared. So my surface area to volume is going to be 600 to 1,000. Now, what you might want to do at this stage is actually divide both of them by the smallest number, so divide both of them by 600 to turn it into a ratio that we're more familiar with. I'm not going to do that now, I'll let you do that one, but you could divide both these by 600, so it'll be a 1 to, and it'll give you the value for that one. Now, what we want to have a look at is actually what happens when we start breaking this down into smaller pieces. So what I'm going to do is I'm going to cut my cube in half. So again, this is not drawn to scale. I'm just drawing this out quickly so we can see what's going on. So I'll just sketch this out quickly now. Almost done. Now, what we should notice with this is that we should have the same sort of external surface area, but we've now got this sort of inside surface here, which has been exposed, which wasn't available before. So anything that was in contact with it couldn't get to this bit because it was inside the cube. But now, because I've cut this open, we've gained this surface area and the same one on the opposite side. So it should have gone up. Now, if you're thinking sort of fairly logically with this one, you can work out the fact that actually this surface here is 10 by 10, so it's 100, and I've got 2 of them, so my surface area has gone up to 800. If you're looking at that going, what has he just said, you can actually break this down a little bit more. So what we can work out with is we've got this face here, which is 5 by 10. And I've got 1, 2, 3, 4 of them. I've then got a 10 by 10 and a 10 by 10. So add those two together and I've got 400. So each of these cuboids, probably the wrong word there, it's 400 square centimeters and I've got 2 of them. So I should have a total surface area now of 400. My volume hasn't changed. And if you don't believe me, you can work that out. But the volume hasn't changed. The volume is still 1,000 cubic centimeters. So if you go through and work this out, we've now got our ratio has gone up. So we can see there is now a change. My surface area to volume has gone up. Yes, Tanishka, you will get such question. This is foundation level maths. Okay, this is not GCSE. This is not difficult. Just working out surface area and volumes of cubic objects or objects like that is maths. Now, bearing in mind at GCSE, any question which is foundation level GCSE maths, could come up on a higher level science paper. Likewise, on a foundation level science paper, they could ask you anything in Key Stage 3 maths, and working out surface area and volumes is Key Stage 3. So all of this could come up on any of the science papers. So we need to be able to practice working out surface area and volumes if it's something you're looking at and going, I'm not sure about that. Now, the other thing we could do, and I'm not going to draw all of these out, but we could, if we imagined that rather than just chopping it in half, I was to slice it up into 1 centimetre cubes, very badly drawn 1 centimetre cubes. Each of these would have a surface area of 6 square centimetres, and it would have a volume of 1 cubic centimetre. Now, I would have in total 1,000 of these cubes. So now when I work this out, my total surface area is 6,000 square centimetres to 1,000, because remember my volume hasn't changed, cubic centimetres. So we can notice we've got a massive change now in our surface area to volume by chopping it up. So when we start looking on the nanoscale, which is what we started looking at up here, what we're looking at is taking big objects and we are actually making them very, very small indeed. Like I said, we are looking at something that is between 1 billionth and 100 billionth of a metre, so massively tiny. This means the properties are going to be absolutely huge because there is so much more of that material in contact with everything else around it. Now, we will look at chemical reactions and rates of reactions later on. That's another chemistry topic. But because those properties change, we often don't need as much, or some materials become more useful. So we'll just go over here for a minute and change colour just so we can see. So increasing the surface area to the volume, we often need less materials. And a good example of this is with titanium oxide, which is one of the main ingredients in suntan lotion. What they found is that actually by decreasing the size of the particles spread further. They have exactly the same effect, but we don't need as much of them in the suntan lotion. So we end up with a much more effective material without actually using very much of it at all. Now, what I have seen in exam questions before is they've started putting in newspaper articles saying things like, but some scientists are worried that titanium oxide particles on this level could go through the pores of the skin and they're unsure of what it would do if it does. And that's absolutely fine because you haven't ever been taught things like that. And what they're asking for is your opinion and being able to apply that knowledge. And it could be the fact that saying we would need to do more research. It could be the fact that, because we don't know what the damage is, but we would have to try and make a decision and justify what we think about that in terms of still using it. And you wouldn't get it right or wrong as long as you came up with an answer that made sense and you had justified it with a reason for that. Okay, so you've made a claim, you've maybe put some evidence down from the question, and then you've reasoned your explanation out. So you've sort of written it as a CER statement. So it's well worth looking at that when we do, and we'll do some examples of that later on. I'll see if I can find some questions. But the key thing here is less materials. A lot of electronics now as well. We've managed to, by working on the nanoscale, we've managed to improve the use of those. In fact, the electronics we've got now have got so small that if we make them any smaller, they're actually going to stop working properly because there's something called quantum tunneling where electrons can move through the electronics rather than around them. And it's the one thing that's limiting the size and the speed that we can make computers in the future, which is why computer technology has sort of changed a lot over the years, because we've almost reached the limit of what we can do with the current level of science. Now, as we research this more, we'll probably find ways around it, and then we'll have another massive revolution and computers will move forward in leaps and bounds again. But at the moment, we're very close to reaching the limit of what we can do, because we've made them so small that it's beginning to have effects on the properties of that. So that's it, sort of nanoparticles. So it is worth having a look. Sorry, it's worth making sure you understand the difference between nanoscale and bulk scale, and the sort of the uses it can have. So we've gone from this idea that actually bigger particles, there's less contact with other chemicals, less contact with the air around them. But when we start getting smaller, we increase that surface area by still having the same volume. So therefore the properties start changing and it can start becoming a lot more useful, even though we're using less materials. That is pretty much me done. I said we'd probably finish a bit earlier, and we have finished 15 minutes earlier. However, I'm quite aware as well there's 4 videos in this topic rather than the 2 or 3 that I've done in the past. What I would say, go back through and make sure that you are absolutely properly comfortable with when materials form ionic bonds, so if it's between a metal and a non-metal. Make sure that you can draw the electron transfer diagrams, and that if you can start looking at doing some of the half equation redox equations for that. Make sure that you can recall and explain the properties in terms of melting points, boiling points, conductivity, and you can explain it in terms of the structure. How does the structure link to it? Do the same thing for small covalent, for giant covalent, and for metallic bonding. If you can get all that, you will nail this absolutely, because I've repeated myself quite a bit in terms of the properties, but that's all the exam questions are asking, and there is only so many exam questions they can ask you on this. Pretty much every question will be one they've already asked in the past. They've just regurgitated it in a slightly different format with different elements. Okay? Yeah, Tanisha, I've got the homework and it looks absolutely brilliant. That's my next thing to email you about when we have a look back through. Well done for going through and having a look and doing that comparison between diamond and graphite. That is good. If anyone's got any questions on any of this, please feel free to email me, message me, and I'll pick it up whenever I can. If you go onto the AQA website, let me just get you the link for this now. There are lots and lots of past papers that you can download free of charge with mark schemes. So I'm literally just going to go through and bring this up now because it's well worth you having a look at some of these. The specification link, and I'll put that in here as well. The specification is what I use to decide what you need to know. And the specification links are all on this page. So I'll leave that there for the specifications. But if you go into any of these, and it doesn't make any difference whether you're into biology, chemistry, physics, the combined or the trilogy, they'll all have slightly different papers for you to look at. But if you go into any of them, and then go down to assess once you click into it, there will be mark schemes and question papers in that area. So for instance, I'll just give you one more link. So that's for the trilogy assessment resources. At the bottom, we've got question papers and mark schemes, foundation and higher. So if you want to have a go at testing yourself, do that. If you want questions on specific topics, just let me know. Yeah, no problems. I'll put that in the, I'll tell you what, I'll put it in the Google Classroom so you can pick it up from there. But otherwise, have a brilliant day, and I will catch up with you Friday, where I will start going through some of the content for next week's work. So next week, we're going to start looking at Physics 1 energy. Yeah, Olivia, I will get you your papers. In fact, I will try and get them out to you today if I can. Okay. Anyway, brilliant. Have a great day, and I'll catch up with you later. Take care.